they are leaders in the quantum optics world. In fact, one of the people I sent an email to this morning, I think I CC'd you. I forwarded something to Jalel and Elizabeth Florescu. And Elizabeth was handling the evaluation of quantum technology for the European Union. And so at some point in reply to them, I said, look, the 5 nations outside the US I think of immediately for more advanced quantum technology that I really know about are China, Austria, Australia, New Zealand, and Canada. And they all have different strengths and weaknesses, and I don't know everything going on in any of those countries, but I do know of some amazing, important things, but that doesn't mean I know everything. But I know they have lots of stuff we don't.
For this presentation today, do you want any introduction, or you want to be just the one who says hello and welcome and I'm here to talk? Because you're going to want to YouTube this and maybe
maybe a few minutes would be good to, yeah. I mean, in the email, I did say a few things.
Yes.
Oh, sorry.
Good morning.
Everyone.
Morning, Dave.
Just wondering if we should have an introduction to Paul Werbos, or if he should just launch off.
It's a little bit early. I think it's not even 8 o'clock yet.
Right.
Yeah. Hey, David.
Morning.
I'm curious, Dave. Have you read Infinite and Finite and Infinite Games, the book?
No.
Oh, it's a wonderful read. I think you'd enjoy it.
Who by?
It's my reading group is studying it.
Is that the James Carse book? Finite and Infinite Games?
Yeah, that one. Yeah. It's only 4 hours. It's a fun read. I think you'd enjoy it, Paul.
Yeah, no, it certainly is relevant to what we normally talk about.
Yeah, no, it's a fun read, as I say. I think you'd both get a kick out of it. It's very methodical.
I have it up right now. I'll take a look.
That's fine.
It's super. It looks like it's written to be super accessible.
It starts off that way.
Yeah. No, we actually had a major discussion where that topic came up. It's also related to interest rates in reinforcement learning. It really matters.
Oh, it's 9/10 of the prisoner's dilemma. Yeah, so absolutely. Yeah.
Well, it moves on to crossroads, which is a technical issue these people usually don't know about.
He has a very interesting definition of what a game is, actually. It requires some rethinking just on page 1 here.
So I'm saying it's a fun read.
Yeah, I'll take a look.
Yeah.
I'll get into it.
Okay, so at some point, I guess I will start recording if people don't mind.
Go right ahead.
And I will do screen sharing. Let me try the screen sharing first, and then the recording.
Oh yeah, sure. I'm not sure if you're.
Yeshua, Holly, and
Okay.
Yeah, that worked, Paul.
Sorry?
That works.
Is it recording?
We don't know if
Yes.
it's recording, but we know we see your screen for sure.
Well, I'm also recording the whole enchilada, so you would need to punch recording yourself as well.
Yeah, I think we see the recording indicator above to the top left because of Mary Beth's recording. So I'm not sure if.
Okay, I'll stop my recording and see what happens.
You wait a few minutes Bernie Woodrow told me it's important to start with things that are interesting but avoidable. I'm very grateful to have a chance to talk about something this important. And since this is the first video discussion ever of this brand new technology option, I think it's important that we have it recorded, even if other people may come up with more precise things later. This is the very first video introduction to a whole new stream of quantum technology. And these 9 slides are all new. And it's a tricky, complicated subject. It's worthy of several hours worth of discussion. Every slide could be a few hours. But there are 2 main things I think I need to talk about. One is this slide, the old stuff. By itself, this one slide could be worth 3 hours of discussion. Because what this is what is quantum information science and technology? And why is it important? What is important about it? I have heard major intelligence agencies, heads of agencies testifying before the Senate. And I've heard Department of Defense people say that quantum supremacy is one of the 2 or 3 most important strategic goals for the whole country. We could talk about quantum supremacy. What are the goals that the intelligence agencies and the DoD are pursuing? This is very serious stuff. But it turns out that's only one of the 3 reasons why this area of technology is important. And by the way, I haven't even said what it is yet. Okay? And that's expendable stuff. People can hear later. I learned about this acronym, Quantum Information Science and Technology, from the days when I was the representative of the National Science Foundation to an interagency coordinating group called QISCOG, Quantum Information Sciences Coordinating Group. The head of that group was somebody in the DoD or intelligence world, but the brains behind it was a very important person named Howard Brandt. And I was almost thinking I should show you his face, because Howard Brandt is one of those unknown people who totally changed history. Howard Brandt was the brains behind these big programs at DoD and the intelligence agencies. And I got to attend because they knew NSF knew something about intelligence systems and quantum theory. And so I was the right guy to represent NSF there. And I still remember meeting Howard Brandt, who really played a crucial role in making this happen. In any event, I think that he was probably the person who coined these terms, quantum information science and technology, about when many, many billions of dollars were being put into this area of research all across US government agencies. The intelligence committees have websites. If you go to the Senate Intelligence Committee, every year they have a world threats open hearing. And the last few open hearings, they have said there are 3 strategic technologies crucial to the future of the country and the world. And the 3 they listed are QuIST, advanced AI, and cyber warfare. And the interesting thing is that we have technical knowledge about all 3 of those. We know things that the heads of these intelligence agencies do not know. There's an information gap. Even the heads of the US intelligence agencies, they know enough to know these are critical. They know enough to know these have important applications. But these are very advanced technologies where there are things they don't know about what the most powerful technologies are. And I am going to be presenting one of those things today in the quantum part. So this is one of the 3 reasons why this whole field of QuIST is a rightful strategic priority. But second box, you folks know very well, I have this little website on a sustainable, intelligent internet. And we've discussed why the future of the internet is crucial to the future of the world, and we're heading in a scary direction. One of the things that the quantum technology offers is cybersecurity beyond what any classical technology can offer. There are new options for cybersecurity, which go way beyond what traditional quantum computing offers you. And it offers new options for cryptography. What I talk about today is going to be one of the levels of QuIST. In this website, this SII website, I have a review of 5 levels of QuIST. What we're doing today in the US is only level 1, like the Quantum Turing Machine. In the computing area, it's only the Quantum Turing Machine, but there are 4 higher levels. And what I talk about today is just one of those other levels. And finally, another reason why this is important, I know this is life or death, most people may not, but the technology and the experiments in quantum information and science are giving us information about how the universe works, about how reality works. And there are people I know who would say, how important could that be? How big is the universe compared to the Earth or compared to my budget? Well, the universe is pretty big. And there's a lot of stuff out there we don't know yet, which is actually more and more important. So this third benefit, the sheer science benefit, is just as important as the other two, in my view. So now, let me go to the next slide if I know how to push this forward. I don't do this very often. Okay, forgive me, I'm going to have to do it. Okay, so now the main theme of what I want to talk about today is true quantum annealing, which is a new option in this quantum information area. It is not the only important option beyond the quantum Turing machine. The quantum Turing machine is what everybody is putting money into now in the US government. This new technology is not the only option. And I'm not even saying it's the most important option. But the reason why I want to talk about it now, there are 3 reasons. First, it's new. We've published papers about other options which may be more powerful, but frankly are harder to understand, and they're already in the literature. This is new. I believe that true quantum annealing is easier to understand than some of the other quantum options. And let me warn you, this is quite a comparison. True quantum annealing is not trivial, but the other new quantum options are even less trivial. But the tools we need to develop to make this real, if we ever make true quantum annealing real, if we ever actually do this RD&D, it will develop tools that are critical to other advanced quantum options. So it's not only TQUA you buy if you get this. Let me mention just a little about the history. This is brand new. Where it came from, it might amuse you. It came from some smart, what? Okay. Doug?
Yeah.
You were saying?
Oh, there was a sentence you used. It may not appear to be something. I lost the last sentence. Go ahead. Don't let me slow
So I'll go ahead. Okay. So what helped me, I guess I could say I discovered this option this year. The way it happened was that people were asking me about the search for extraterrestrial intelligence. And there's a guy named Pete Warden who used to run NASA Ames, maybe the best NASA administrator in the whole system until he retired. He's running a breakthrough research project out of California. And he's discovered some strange things he saw in the sky. And people asked me to look into it. And when I looked into it, I was amazed. I looked at the technology they're using now to scan the sky. And it turns out that if quantum annealing works, you can use it to get millions of times more information from existing telescopes, radio telescopes mainly, in any search of the sky. So this is good not only for SETI, but for any technology that looks for things in the sky. You can think of a lot of possibilities that might be interesting of things you could look for in the sky millions of times more efficient. That struck me as very interesting. I was very excited when I saw that quantum annealing would let me do that. I owe thanks to Dave Clement, who is right here, right now. From this group, Dave Clement put me in touch with the people of D-Wave. And I thought that this Canadian company, D-Wave, was selling a QUA box. And I was so excited what I can do with his box that they haven't thought of. But then when I studied the box, it doesn't do what it's supposed to do. I studied in great detail all of the literature on both sides of D-Wave. And the bottom line is, yes, they're doing something useful. Yes, they're a good company. Yes, they have important products. But no, it's not true quantum annealing. And the final bottom line is, based on what I know of the physics, which they don't know, and based on the technologies I learned at NSF, I can see how we can do it right. It is possible to build a true quantum annealing system. No such system exists on Earth yet, but it can be done. I will show you what the path is for getting there and what some of the amazing applications will be if we go ahead and develop this kind of technology. Any questions before I go on? I got to explain what it is first. So, okay. Now, what is it? And what's the difference between quantum annealing and what we're doing today? When I was working with these QuISCOG interagency people, I learned that almost all of the US government investments in quantum computing are based on a concept called the Quantum Turing Machine, due to David Deutsch. There's a thing called the Fermi Prize. They gave 3 prizes for the invention of QuIST. The #1 prize was to David Deutsch, who wrote the classic papers on how to build a quantum Turing machine. It's the basis of what we're funding. It's good stuff. A lot of money is going into it. It works. And this new concept of quantum computing is based on a specific view of how the universe works. And the funny thing is, I don't believe this is the truth of the universe. I just believe it's a good approximation, but it's the best approximation we have today. A huge amount of empirical work has gone into building quantum computers based on David Deutsch's vision. A lot of research, technology, and proof and experiment. And all of these experiments are really based on this theory of how the universe works. According to this theory, we live in a multiverse, which is to say we live in a space-time continuum where time is one dimension and space is X. It's a point in the multiverse. It's this infinite dimensional space called Fox space, which he calls multiverse. By the way, David Deutsch has very nice YouTube, easy to find, on multiverse that it explains a lot of the intuition behind his theory of how the universe works. I am proposing that we use his theory of how the universe works even now for the next generation of what we build. Okay, this is a more or less good enough model if you fix up the measurement assumptions a little. So the idea is we live in a Fox space. We live in an infinite dimensional space with multiple copies of all of us. And this bottom line, this is what the quantum Turing machine is really based on. David Deutsch basically said, you think that parallel computing will give you a lot of power. You think you can get a lot more power by putting 1,000 cores on one chip, 1,000 processors in parallel. That'll work. But you can get even more power if you use trillions of copies of the same chip in parallel using quantum superposition. So David Deutsch's concept of quantum computing, you can do massive quantum computing by doing millions of copies of the same chip, computing different things, working in parallel with each other. Millions of streams of computation physically in one chip, but it's what they call a Schrodinger cat. There are millions of copies going all at once. And when people first heard that, they said, this is crazy. How can you have 1 million copies of a chip? How can you have a macroscopic Schrodinger cat? How can you have millions of copies of the same chip in different states doing different computations and put them to work? He proved theorems saying you could, and real engineers have built these things. There are working quantum Turing machines out there today. When I talk about 40 qubits, that's about a typical number. They've proven and built systems with 40 qubits. That's like 1 trillion copies of the same chip, all working in parallel. So this is the Quantum Turing Machine. This is Gen 1, and I'm trying to do better. Okay? Gen 1 can do useful things, but it has certain limits. So I probably should say just a little bit more about that Schrodinger cat. This is a slide I did for physicists. I used to run the quantum modeling program in engineering at NSF. This is the program that developed the advanced quantum theories and models that you use to build real electronic and photonic systems. That's what I'm talking about. Can we build a real electronic photonic system using quantum principles? And I ran the program to do that. And everybody doing research in this field would be sending proposals to me. And they all had different theories about how the universe works. I've studied these theories in great detail. Let me just say, David Deutsch beats all the rest. Okay, I'll just leave it at that. This is something you could talk about for many university courses. But the bottom line is David Deutsch's theory works. It works for electronics and photonics. It's been tested, and it makes the most sense. But that doesn't mean his quantum Turing machine is the best. Even if you believe his theory of how the universe works, even if you use everything we learned, one can do better. So the quantum Turing machine is based on standard Turing machine concepts. If you're big in computer science, it's what we call alpha zero complexity. There are reasons why using binary variables is not as powerful as continuous variables. If you're a pure mathematician, what you can do with digital discrete choices, there are all of zero countable choices. With continuous variables, it's all F1. And we actually get up to like all F4 by the time we're done with what we can do with advanced quantum mechanics. I'm only going to be talking about one of these advancements today. When I look at what they're doing with quantum Turing machines, they're using standard computer science approaches to write programs. The philosophy is the physicist will build you your machine. You have one group that'll design the quantum Turing machine following David Deutsch's rules. And then a totally different group of people will say, I will program this machine. I will be a computer scientist. I know what a computer is. I know how to program it. And they have algorithms specific to this kind of computer. And the purpose of this activity is we will execute a program. That's what they're trying to do. And that's all they achieve. Now, the question is, can those traditional QTM people solve problems like minimizing error or maximizing utility? And in the real world of engineering, there are many times we want to minimize error or maximize value. And if you want to minimize error or maximize value, that's an optimization problem. That's not a Turing machine problem. And can you do that with a quantum Turing machine? And the answer is you can, but not well. There is a YouTube talk out there. This is the only website I think I put in these slides. This website is up to date and exciting. It comes from 2 days ago. The most up-to-date review anywhere in the world with all the world's leading experts on what you can do with a quantum Turing machine to solve optimization problems. And the bottom line is when they use quantum Turing machines, they have lots of ideas and they basically don't really work, which is to say they have traditional Turing type algorithms, which can get you like a polynomial speed up in optimization, but the cost exceeds the value and it's totally useless unless there's some future research. And a polynomial speed up isn't much anyway. It's not buying you factors of 1 trillion in optimization. So the bottom line is the quantum Turing machine doesn't really solve these problems. However, my proposal for true quantum annealing is to use physics, the actual physics of annealing. It's not just computer programming. It's the design of the computer itself. We're not just buying a machine over the fence from a bunch of people designing Turing machines. We're building a new machine using the same physics, but a new type of machine. And that's what I thought D-Wave is doing. And on a good day, it sounds like D-Wave is doing this kind of computing. I thought it was. It looks like it in some of the advertising. I was really hoping it. And for a true quantum annealing, let me define true quantum annealing is when you use the physics to explore trillions of choices in parallel, like a queue of 40, like 40 qubits, real qubits, really exploring trillions of choices in parallel. And it can be done. The physics allows it, even though D-Wave isn't yet doing it. I should put in a caveat. If you go to this great, wonderful review, if you go to this review, you can tell there were NSA people participating, as well as people from all around the world. It's based on a great literature survey. I remember someone once told me, hey, that friend of yours, has he done a complete literature search? And I said, he's probably read every email written in the world on this subject in the last 2 years. If you want a literature search, you should see the way they do a literature search. They have a real good literature search, unbelievably good. But at the end of the day, there's not that much there yet, but there is one technique they knew about called Aurora Kale, which I think is actually a special case of quantum annealing, but it's only for a certain quadratic case. So the bottom line is D-Wave has wonderful values, but it isn't making full use of the physics. It is possible to do better. D-Wave is a great foundation to build on, but they don't give us true quantum annealing yet. And the question is, how do we get it? And why don't they have it? I owe great thanks again to Dave Clement for putting me in touch with the 6 literatures. D-Wave is not a simple place. There is a huge community of people, and there are real applications. But if you trace it back, what the company D-Wave sells, it's got outer interfaces, which are very important. And these outer interfaces will always be useful and profitable, and we will need them. But what they interface with, the quantum annealing box at the center of the system, the core of the system, what is supposed to give you quantum power in the D-Wave system, the inner quantum annealing box is based on a classic paper by a guy named Bianchi. And when I saw this paper, I was really excited. I know Bianchi. I know that name. He knows real physics, the Bianchi identities. Well, maybe it's a different Bianchi, because what's wrong with it is it doesn't do justice to the physics. In this quantum annealing core, this is the core of the D-Wave box. It represents reality as a set of n signals. Okay, so you've got n continuous numbers, and the idea is to find the optimal value of n numbers, n continuous numbers. And you assume that the quantum core is governed by a Schrodinger equation, and this is basically it. It's basically a quadratic function. Okay, and this basically comes from what's called the Ising literature. And if you look at the literature on Ising lattices, a lot of work has been done in this field in physics. In the way he does the quantum annealing, the way he does it is he adjusts the coupling constant alpha. So you start from no coupling, and the way you anneal is with actual alpha. But the problem is you're cycling around. Now, this thing conserves energy. So what it does is whatever your initial values are, it comes up with different solutions that have the same energy. They're not any better than what you started with. And how the hell can you expect to find the least energy solution if you use a dynamical system that conserves energy? If you know the physics, you know that isn't annealing. Now, as it happens, I know what annealing is. I know it because we did a lot of annealing in NSF and even before that. Annealing is an important concept if you ever build solar energy systems. I just happen to build a few programs in that area. And in real physics annealing, you know, what you do is you heat it up and then you cool it down. It sheds heat. And because it sheds heat, it goes to a low energy state, which is what you want. You want to go to a state of low energy. That's the minimization problem. We know how to do that in physics, but that's not what they're doing now in the box. They're not doing that. So my basic idea here, it's very simple. It's obvious when you know the physics and you look at it. The obvious solution is to take your inner box and hook it up to a thermal reservoir. You need wires anyway to connect to the outside world. Hook them up to your external heat source and let it behave like a solar cell. And we do this with solar cells. You hook it up to the external reservoir, let the heat leak out so it can find a state of zero energy. What's more, if we use the right kind of quantum hardware, which has low decoherence, you really can maintain 1 trillion solutions in parallel. You still have the Schrodinger cats. And this is less sensitive to decoherence than the normal quantum Turing machine. The normal quantum Turing machine, you have to worry about noise coming in and destroying your program, your initial conditions. Here, your program is already hardwired into this 8-0 matrix. And D-Wave already has a system for creating these 8-0 matrices. It has a whole gigantic input apparatus to translate a problem into this kind of a matrix. We can use the same machinery, only we can actually use real quantum annealing to solve the problems which D-Wave is already setting up for us. The only thing we need to change is the box on the inside. So if you use the right hardware and you shed energy, this is within the realm of physics. I'm not saying it's easy. I'm not saying it's not a research project, but it helps if you start with the right physics. If you ask the wrong question, you'll never get there, and they're not getting there. They've spent lots of time working on the wrong question, but there's good reason in physics to believe we can answer the right question. We can do a stochastic search of trillions of possibilities, just the way a quantum Turing machine would do. It's possible to do true quantum computing with this kind of a minimization task. But it is important that the hardware must be low noise. This is not as sensitive to decoherence as our present generation is, because there's no need to preserve initial conditions, but you still want low noise hardware to do it. But we have low noise hardware. We certainly have already developed it. And the beauty of the QTM thing is we can use the same hardware. Okay, so the bottom line is, if we want to build a true quantum annealing box, if we want to build this kind of box that you could put in the inside of a D-Wave system, replace the old box, which is a classical noise computer, and the inside of the D-Wave system to solve the same problem, you can use different kinds of hardware as long as you're willing to interface with a thermal reservoir, stick wires to the noisy environment. There are 4 areas of hardware that need to be developed. If I were doing this for the US government, I would certainly make sure there were 4 parallel threads. And you might say, gee, that's a lot of threads. I promise you, in the existing funding on quantum Turing machines, there are probably like 12 threads getting money in parallel. So what I'm proposing is not that we create these new threads. I'm saying that we pick out 4 of the existing threads and apply them to this problem. The number 1, I'm looking at Yeshua. Number 1 is Yeshua, okay? His presence is not a coincidence. And we must all pray, and God is important, but we also have some hardware here, okay? And that hardware happens to be number 1. One of the things we can use that D-Wave is not using is quantum optics. For a really effective research program that also benefits basic science, we can prototype design concepts in quantum optics with a level of accuracy and control which simply is not available with any of these other technologies. This is really important. I mentioned Yeshua's work with Carmichael's group, which right now is the visible lead in the world, but there are other groups we talk to that are important that we need to coordinate with. So we need to use quantum optics as a platform for developing the math and proving out the concepts. But then there's a second hardware platform called SQUIDs, superconducting quantum interface devices. And I know this technology very well. I used to live about a mile away from where it was developed in Maryland. Okay? And that's why I could recognize the office in that video on QTMs for optimization. I recognize the bloody office because I've been there. I lived 1 mile away from that place and visited it often. They invented this concept, I think the guy's name was Kane, for superconducting quantum loops. This is one of the techniques for quantum computing, which was pioneered in the US, but the US does not have the lead anymore because there are people in China who learned about it. More precisely, China has the most advanced industrial grade quantum technology program in the world. China, working with Austria at times, China is way ahead of the US in areas which our intelligence agencies do not even know exist. And I've been to these places in China. They are unbelievable. This stuff is led by a guy named Pan Jianwei. And I said in a previous talk, Pan Jianwei, his face should be familiar everywhere. He is important to this whole technology in the whole world. He's had conversations with Xi Jinping directly, who has given him full support for this massive QuIST program in China. And they are primarily using SQUIDs. And I have seen some of this apparatus when I visited Tsinghua. So I have seen and visited, they were mad when I took pictures, okay? But I've taken pictures of devices which do not exist in the US. And they were pissed that I showed them by accident on Facebook. They have very powerful technology, and you can do this quantum annealing with that technology, okay? Now, D-Wave is using SQUID technology. Somebody told them this is a good technology, and it is good. But the problem is they don't use it the right way. And the reviews of the hardware used by D-Wave show that D-Wave is operating these SQUIDs in a regime where like the voltage is not right and they're not getting the right noise reduction. So people are upset. It has a decoherence problem. It has a noise problem. It's not a true quantum annealer. One of the reasons it's not a true quantum annealer is they're not using the SQUIDs the right way. Everybody in the QTM world knows how to use SQUIDs the right way. The review papers that tell you how you use a SQUID, they're not using the SQUID the right way. There are lots of people who know how, but these computer scientists who are working on this don't know that physics. It's the problem. So the bottom line is, with quantum optics to get the math really right, with SQUIDs, that's important, but there are two further design options we should start working on now, even though they're further away. And you might ask why? Well, there are good reasons why. The other options we should be exploring now, one of them is the use of quantum dot arrays. I mentioned the Samsung television, the QLED television, but I learned today I really shouldn't underestimate the new LG, also from Korea. So there are two big companies in Korea who have learned how to use quantum dots, millions or billions of processors in a physical box you can fit in a living room. So instead of having 40 qubits, what happens if you have 1,000,000 qubits? You would not believe, if 40 qubits gives you the universe, what the hell do 1,000,000 qubits give you? Well, they give you quantum supremacy. If you want quantum supremacy, this is supremacy. And so now Samsung's TV are not ready to program. You need to develop the interface. But the core objects in there, these quantum dots, can be used for qubits. When I was in SF just now, I remembered there's a guy named Raymer I funded who was working with quantum dots. Raymer showed you can use quantum dots in quantum computing. So if you take what Raymer learned, what we funded, add some control, this will give you a breakthrough in quantum annealing way beyond what people are dreaming of. And then the fourth of these, high-speed digital design. This is electronic. This is what we do to get gigahertz frequencies on a cell phone. It's a whole new area of electronics. Most electrical engineers don't know it yet, but there is a textbook that I sent you a link to. And if we do this, the main value of this, it's more powerful than the quantum dots potentially, but the main benefit is it leads you to other technologies beyond the scope of this talk. So if I were building a real quantum annealing research program, I would make sure we included experimental implementations in all four areas. I'm probably pretty close to the end on time. Let me see, is there any, oh yeah. So there are 3 levels of quantum annealing. I sent this out in what I sent you in the links. To develop true quantum annealing, you have to go through 3 stages. The first one is relatively easy mathematical, where the user goal can be written into H, which is the way D-Wave normally does it. The next way is internal coupled scoring, and then the quantum annealing of things, which is the 3rd stage. The physics says you can do all 3, but to do them in the real world, I think step 1 is prove theorems about how you interface with thermodynamics, okay? We know what thermodynamics is. This is not impossible, but stage 1 is to just work out the equations to show, like with a quantum optics embodiment, that you really can make this kind of true quantum annealing work, that you really can get the qubits you want to get. You can do it, at least in this case. Start with the easy case for which the math and the hardware exist, and then work your way up to quantum annealing of things, which is the final stage. Quantum mechanics governs physical objects. This is the important point for the quantum annealing of things. Quantum mechanics applies to physical objects. It's not only computing that can be put in a state of quantum superposition. The physics is clear. The physics has been tested. I didn't used to believe it, but over 20 years, the experimental data has been overwhelming. I didn't believe it, but I've been convinced, and I've looked at the math. It's possible. It happens. So what can you do if you can put physical matter in a state of quantum superposition? And the physics is clear you can. If you do that, it relates to observing the sky. You have radio telescope settings, and you can put a radio telescope in a mixed state. There are control parameters in these telescopes which say where it's looking at, and you can use quantum annealing of things to create the observation settings which get you the most interesting results. So if you're looking for an ET signal, or you're looking for a bad missile trying to hit you, either way, you can set it to find the thing you're looking for, the needle in a haystack. You can find the needle in a haystack with 1,000,000 times more efficiency than any classical technology. So that's interesting. There's also an application I call quantum bromium. If you have a chip and you're looking for a bad backdoor, we already know how to do classical bromium. You take that suspicious chip, you subject to a whole lot of probes, and you see what happens. That's today's best technology for detecting backdoors in chips. But instead of 1 probe, you can do 1 trillion probes in parallel. You can find that bad needle in the haystack. This is a very important application to find backdoors in suspicious chips. This is not a small application. You could also try it for drug discovery and for airplane stabilization. And maybe I need to stabilize my talk. Thank you for your patience. I guess I could stop sharing.
Paul, can you tell us a little bit about what the relationship is between this sync of, so basically with quantum annealing, you have a problem that you want to solve. That problem has a certain set of parameters that essentially specify what human beings understand to be the main axes of interest in that problem. We need to map that into the quantum realm. And you're suggesting we do that by hooking up a quantum annealing system to some sort of physical system, such as a radio telescope or some other mass, you called it, which is adiabatic or has entropy. Is there another challenge in this, which is to find matches between problems that we're interested in solving and in masses that characterize that the elements of that problem in some way? Or is it deeper than that, in which we actually have to do something else? Do you see what I'm trying to get at? I mean, how do we characterize real world problems as quantum annealing problems?
So maybe,
Or is that a broken question? Sorry.
no. It's a very important question. Whenever we apply the quantum annealing of things, we have to study how do we map the thing to the box. That's the, for anything, you got to figure out how I'm going to map the thing to the box. And for each of these 4 application areas that I've looked at, there's a whole lot of additional material on how you do that mapping. It's important. But let me say, as a first step, there is a cheat that you can begin to use. And the cheat is that D-Wave already has a market. Okay? And even though the box they have is not a true quantum annealer, nonetheless, it is an optimization engine. And when people use it, they have to map their problem into the kind of optimization that I thought D-Wave was selling. And probably a lot of those people think it's already selling it. So people have done a huge amount of work on many applications where the work has already been done in many applications. So that's part of the answer. This is a major industry, but all it needs is more horsepower in the box in the middle of the industry. The other thing is, for these 4 specific applications, these are just examples. If we didn't have D-Wave, if we were doing it de novo from scratch, even at NSF, we would say, pick a really good application. In fact, I was even discussing neural nets with the Chinese Academy of Sciences. And they said, even to develop this whole giant area with an international initiative, we need to focus on 2 or 3 driving examples to develop the general technology. And these 4 driving examples are cases where I personally have looked into how you do the mapping. There are interesting ways to do the mapping. I must have about 10 emails to the people in Missouri and also to the people who do observation technology that I have a link to. We have an idea how to map, for example, radio telescopes. We know in the SETI operation, we have the papers. They've published exactly what all the control authorities are. And you use those as inputs, and we have flowcharts on how you map it. But the bottom line is you have descriptors of the plant that you're trying to control, and you send them back as instances of U. You have to build an interface to go from a proposed optimum for the vector U to the controls. Okay, so you have to have a mapping from, so let's say, supposing you have 40 real qubits. Suppose this vector U has 40 components. If you want to apply a quantum annealer to your radio telescope, you need to find out how do you want to control your telescope. So you need to put in a little box which inputs these 40 numbers and outputs an interesting control setting. And you want to find a mapping which represents what might be interesting control settings. So there are like 40 bits you can play with to define a control setting. And the user, yeah, you need to define the mapping that inputs the 40 bits and outputs the control setting. And the task is to come up with interesting control settings. But the thing is, most of these people have controllers already. So it's not that hard to come up with interesting control settings. The problem is to choose them. And so basically, it's a really simple interface problem. And the same thing applies to all of these. If you build a quantum bromium system, even today, with today's sandbox, you've got to come up with probes to test the chip. There are already programs to test the chip. Okay, so index your probes. If you have 1 trillion possible probes indexed by 40 binary variables, use those 40 binary variables to try all 1 trillion possible probes indexed by those variables. And the same thing with all of it. But each application will require, for that application, you need to do the interface from the U vector, what you're optimizing over, to the actual controls of your system. That is one of the tasks. And we've looked at that a lot in the SETI example. We've got a bunch of papers on how you do that.
You use the word interesting, which is interesting. How do you assess interest?
Well, in the case of SETI, one thing you might do is go talk to Pete Warden, who's scanning the sky for ETs. And by the way, there will be people looking over his shoulder who are scanning the sky for other things, which might actually be interesting. But Pete Warden, he has spent years of investment trying to figure out, how do they set their radio telescopes? Where do you look? They have spent years trying to figure out what are interesting places to look. And they have a huge menu of choices and things they've been agonizing over. Basically, all you do, it's almost like the quantum bromium. You just make a list and you index it by binary variables. You know? So you do need domain experts to give you a feeling for what might be interesting places to look. But the interesting further development, which D-Wave knows about, is if you start with a list of 1 billion possibilities, and you certainly discover that certain ones are the most interesting, you can use that experience to give you a clue for what you might look next, because you can do this again. You're not limited to one iteration. You can look again. And if with your radio telescope, looking for signs of strange life, if you discover that all of the interesting signals come from red dwarfs, why then you can reprogram it so that your vector U points to places you might look in red dwarfs. You can subset and do a second stage search that way. And I think the practicalities of this are known to the D-Wave people.
Right. So when we talk about quantum annealing, annealing is really kind of like a very rough analogy. What we're really doing is, if I understand it correctly, we're evolving the Hamiltonian of our system with that coupling constant A that in the model in your previous slide, and we're keeping it in the ground state. We're doing it slow enough. We're moving that alpha slow enough that we always remain in the ground state. Right, so it's not really like an annealing so much.
That's what D-Wave is doing.
Yeah, that's what
I'm
traditional. Right, so you're saying something else. You're saying let's allow the system to be in excited states, and then somehow we'll cool the whole thing to absolute zero or whatever, and make sure there's no degenerate ground states somehow, and then somehow while it's at absolute zero, still read the state somehow.
Well, okay. I don't think you need to go to absolute zero.
Or cool it to a ground state.
But the bottom line is, the existing approach, you start with an excited state because that's basically all you got. You know, if you've got clever designers and they can guess the solution, then that might be close to the answer, but then you already know the answer. And that depends on knowing the answer. And there are a lot of games people play to try to use quantum tunneling. In fact, the paper that really made it clear to me that they're not doing true quantum computing is when they analyzed how this system works. There's a lot of good literature on how the core system works in D-Wave, and papers like Bianchi. And they talk a lot about how you do quantum tunneling from your present solution to your next solution. And in true quantum computing, you aren't moving from your first solution to your second solution. You're running them in parallel. They're both alive. And the reason why this doesn't work very well is that we don't know how to set it up in an initial state, which is all where you want to be. So how do you get rid of the junk? And that's what physics annealing is for, is to get rid of the junk by hooking it up to a reservoir. And it doesn't have to be absolute zero by any means.
Yeah, but to be clear, you're saying we allow the system to couple, we allow the system to
Yes.
decohere to the outside, and then you cool the entire surroundings.
Well, we have a
literally
coupling.
cool.
We have a coupling to the outside, and then there's no doubt that the value of this depends on what is the outside like. If the outside, in the most extreme case, as you say, if the outside is just a near zero reservoir, a cryonic, and we know how to build these things. It's not as if liquid nitrogen is all that rare. If we immerse this thing in liquid nitrogen, as they do with a lot of quantum computing kind of systems, then you could just simply put this at a normal temperature and have the heat escape. And this is basically how a lot of present quantum computing works. But on the other hand, if the outside reservoir is truly stochastic, it might not be as bad as that. Because if you're slightly hotter inside than the outside, heat wants to flow out. And if the outside temperature is below where you want to be, you're fine. But there's a whole lot of engineering needed to implement this, absolutely. And step one is the mathematics that really spells out this thermodynamics for the simplest case. And again, the simplest case is not the quantum annealing of things. The simplest case is what D-Wave sometimes says it's doing, which is the traditional quantum annealing, where you're just finding a minimum of their existing Hamiltonian. If you know what this Hamiltonian is, if this is your whole problem, that's an interesting special case already. And that's the one we would start with if we get something going in this direction. And I think that's worth doing. But that is step one. Quantum annealing of things is level 3. In fact, maybe I should have said more about these levels because they really are important. These 3 stages are important. That there is basic thermodynamics, which can be done. Probably what I would do is just steal a lot of the existing work on quantum computing, look at the temperatures they're using now, you look at the hardware they're using now, compute the thermal flow. It isn't so deep, it's known physics. It's heat flow, for God's sake, okay? So it's not that deep physics. But then for the advanced application, when you start doing it on a physical plant, that's another level beyond that. A lot of what D-Wave does is sort of in the middle because they have an input scoring system. People are using D-Wave today with what I call internal coupled scoring. This is part of the D-Wave paradigm. And if D-Wave had a perfect box in the middle, they would already be at this level. The only thing wrong with D-Wave right now is that they don't have the right box inside. But they've done a lot of this work. But yeah, and by the way, this is not the easiest form of advanced quantum computing, but I think it's the easiest to understand, frankly. When I talk about doing a simple thermodynamic coupling with a quadratic Hamiltonian and a simple heat flow with hardware well known in quantum computing, that should be understandable to a lot of people.
So that actually leads into my question, Paul, which is there's been a lot of work in AI recently around explainability. And one of the critical problems that we face with black box systems in AI, and I'm fairly sure that quantum computing is in the black box realm, is that although the system has very good predictive power, it doesn't really give you an understanding of what different interventions will actually achieve. In other words, it can predict very accurately, in the optimization problem, it can tell you what the optimal result is, but it can't tell you what the effect of changing the system in some way will be, if that makes sense. So it offers an insight as to where maxima or minima might lie in general, but it doesn't really tell you what's nearby. It doesn't give you a map that you can use to navigate and to essentially plan how you're going to solve your problem, given that we know that there's a minima there, we can't get there for engineering reasons, we need to go somewhere else. It doesn't really provide that kind of insight and mechanical kind of what to do next set of information that we can use. Do you have any comments on that?
That is a very entertaining starting point because it leads to many, many interesting things. The question is, which one do I start with? Certainly, there are a lot of people studying many explanation issues with AI and the internet already. That's already an hour-long topic. But this is a special case. So let me start out with a humorous example of how does that play out here. Suppose you build a quantum annealing of things device for looking for extraterrestrial signals. Pete Warden's group has reported seeing a signal from Proxima Centauri. This is written up in Scientific American. And on the face of it, it looks like it's a signal that could only come from intelligent life. And they're busily trying to reassure people, no, don't jump to conclusions. But I've looked at the details. There is no basis for not jumping to conclusions, except for the fact that, gee, we want to check this out because it will blow people's minds. Some of what they've said about this discovery reminds me of what Donald Trump said on the morning when he said, don't worry, COVID won't amount to anything. Don't worry, it's my job to calm you down. Okay, so after Pete Warden observed this, now let me rephrase your question. What if we build a new box and you turn it on and you find 100 real extraterrestrial signals, stronger and clearer than what you found before? Will you be able to explain what you are seeing and what to do next? Well, if we see 1,000 extraterrestrial signals, there will be a new explanation problem. And I would rather be in the light than in the dark. I would rather see this thing that needs explanation. I would at least want to be able to find the signal. And then the next step is, yes, the minute we detect a signal like that, we got a lot of explaining to do, absolutely. But the first step is to detect the signal. As a general matter, now to be more formal, it is intrinsically interesting to find the needle in the haystack. But when you have found the needle in the haystack, in all of these cases, that always is an opening to a further industry, a further activity. And that's why you do it, because it is an opening to more stages down the road. But at least you want to be able to see what's out there to begin with.
Let me try David's question a little different. It's one that I've been thinking about, and this is not to demean any of the discussion here. I mean, this is seriously interesting stuff, and I'm just taking my initial steps and trying to understand it. But there are a couple of things that kind of jump out at me, and let me try them in a couple different ways. So with this approach, are we essentially creating a whole bunch of, a very large number of black boxes? So when
It doesn't have an attachment.
Well, why don't you use your iPad?
when we look at, when we look at deep learning models now, in some sense, I think there's a recognition that they're kind of overfitting the data, that they don't have necessarily an explainability quotient that's high. And, to what extent are we kind of going to wind up in the same position? So, maybe instead of running a GPT-3 model in, 3 days, it's now going to take 3 seconds.
So
Or another way of,
Yeah.
of trying to phrase it
Yeah.
too is, the types of problems that we've talked about here are more kind of cross-sectional problems, not so much time series problems. So I guess I'm wondering whether this new technology would allow the development of, kind of like David was getting at, much more causally based structures that we can't do now. I'm sorry if the
So,
stuff is really
yeah, no,
rambling.
I understand what you're saying. I didn't start out by saying we're developing a more powerful system to do what neural networks do. This is a different set of tasks. On the other hand, I do have a published paper on how you use this to build more powerful neural nets. And that was one of those complicated things I said I won't talk about because it's too complicated for people to understand and too hard for today. So in a way, I'm proposing the quantum annealing as a way to make a huge advance, which is incredibly useful, but then it opens the door to more technologies and more questions. So let me narrow that down a little. In these applications, I've suggested that people plan to run the system for no more than 10 minutes at a shot. Okay, so that the idea is to have a start time when you turn on your optimizer, like you're hooking up to your D-Wave box, your super D-Wave box. You turn it on. It controls a physical plant, and you set it to end and score at the end of 10 minutes. You optimize what you see 10 minutes after your starting time, so you don't get into the question of what happens when you leave the world a mess tomorrow. The idea is you want to decohere in 10 minutes. It's kind of like defuzzification. In defuzzification, you have many options, and then you do a defuzzification and you pick one at the end of 10 minutes. That contains the implications in time, so you don't have to worry about it. Even if you've got an airplane that's maybe about to crash, there's a whole lot that can happen in 10 minutes when an airplane is about to go unstable. And being able to stabilize it in that 10-minute period is a huge advance in many ways with all kinds of aviation. But I propose that for the beginning, we try to limit it to 10-minute runs so that we don't get into the complexity. What happens if we let the entanglement run further? What if we try to use a true quantum annealer to change not the future of the next 10 minutes? What if somebody says, I'm going to use it to change the next election in 2 months? Then you're going to start having problems. So there are a question of what are good applications and bad applications. I have focused here on applications which are very big, very important, already enough to justify the effort. For God's sake, quantum bromium by itself is of huge economic importance in this world. Dave Tromley has told us about what backdoors, bad backdoors in chips can do to the whole country. This is a huge application. So these 4 are focused enough that they're worth the effort, and they don't give us these other entanglements. But on the other hand, if we do develop this technology, there are people who will say, wait a minute, can we take it further? Can we go into the twilight zone? Well, we're already doing that with SETI. But with SETI, you're trying to explain what the rest of the universe is doing, which you got to do anyway. At least we know it's there. If we have an explanation problem, but we don't have this time series problem you're talking about. Time series problems are utterly essential for intelligent systems on Earth and for economics. When we deal with interest rates and crossroads phenomena, time series are very important And you might well say, what happens if we start to apply this kind of technology to the kind of neural nets and intelligent systems which can do time series and planning over years of time? And the bottom line is, I'm not talking about that today. That's a real issue, but I'm not proposing a program in that area. I'm proposing a 10-minute program. We got enough work to do with a 10-minute time horizon.
Well, speaking of minutes, we are over time. Jeffrey has his hand up, and anybody who has a question that we won't have time for, have to leave, put it in the chat and we will get back to you on your questions. So Jeffrey,
Well, thank you very much. My question goes to what you just started to imply, and that is this quantum annealing approach to quantum computing applicable to such problem areas beyond physical systems, such as climate change or avoiding nuclear war or economic development?
The quick answer is yes, it applies to all these things. A next immediate reaction is I've been proposing that advanced internet technology, which this is part of, could be developed in a new UN open, transparent office, this Office of Existential Threats. And I think it is important that some of this stuff be open and transparent so that we don't get really weird things in the dead of the night, so that we know what we're doing. And I hope that there will be an international agreement that will try to understand what we're doing in a scope of 10 minutes before we try to take it further. For nuclear and climate, the implications are very different. For nuclear threats, I've even suggested we need a third new division after we get climate and internet. The UN could be doing new types of things on nuclear threats. There are issues with nuclear threats that haven't been fully accounted for. This is certainly aerospace technology. The fourth application I mentioned is keeping your airplane from crashing, but there are other things that could crash. Basically, this is applicable to any aerospace control decision of any kind, which could exist within a scope of 10 minutes. And you probably know what can happen in 10 minutes better than I do.
Yeah, I'd just like to know what the S&P 500 index is going to be in 10 minutes.